Hey guys, welcome. In order for you to understand this video, you need to have first watched my videos on the introduction to complex integrals and the evaluation theorem for complex integrals. As you'll see shortly, without watching those two videos, this video will not make sense. With that said, as per promise, in this video, I'm going to offer you a second perspective on the path independence of contour integrals. And I say second perspective because in a video I made a while back, I used parametrization to prove that contour integrals are path independent. But this video comes with a bonus, which is showing why the closed integral will have to have a value equal to 0. We showed why the closed integral has value equal to 0 in the corollary at the end of the video on the evaluation theorem. Alright, with all this said, let's start this video by looking at this visual. So we have a point Z1 here and a point Z2 here, and two contours C1 and C2 both positively oriented. Yes, C2 is in a counterclockwise direction. Think about why, right? Think about it. Okay, now let's first assume path independence and show why the closed integral will have to equal 0. If we assume path independence, then this will have to be true, which is the integral over C1 is equal to the integral over C2. That's what path independent means, right? Okay, but then we could form a contour C by taking C1 and adding it to C2. That's to say that C would start and end at Z1. It would first go along C1 in the same orientation as C1, but then once it gets here, it'll come back to Z1 against the orientation of C2. And then from what I said in the intro video, if you go against the orientation of a certain contour, then the value you will get will be the negative of the value of the integral in the positive direction, right? That's to say that we can write this, which is the integral over C will have to be the integral over C1 plus the negative of the integral over C2. Again, because we're going in the opposite direction of C2, right? And so since the integral over C1, as we said, is equal to the integral over C2 because we assumed path independence, this is equal to this. So when we subtract them, we get 0. And so this is our second perspective on why the closed integral will have to equal 0. Okay, now the other way around, which is assuming that the closed integral is equal to 0, which we already saw again in the video on the evaluation theorem at the end in the corollary, right? We saw that that the closed integral has value equal to 0. But if that's true, then that means that the integral over C will have to keep this minus sign, and it'll have to look like this. We can break it into two contours like this. But again, that minus sign would have to stay for the integral over C. So this is equal to 0. But then if this is equal to 0, this is automatic, right? Okay, cool. All right. I hope you enjoyed this video and you liked that. And keep watching. Take care.